Hey there, and welcome to this explainer. Today, we're exploring a fascinating piece of aerospace design that's literally hiding right in plain sight. We're diving into why the color of a rocket or a satellite is never, and I mean never, just an aesthetic choice. It is, in fact, a life or death engineering decision. As you're going to see, the visual spectrum of space exploration actually serves as a literal blueprint of human ingenuity and some seriously extreme survival constraints. So, if you've ever watched a spacecraft sitting out there on the launch pad, you've probably noticed a whole lot of bright white paint. It's an iconic look, right? But have you ever stopped to wonder exactly why that is? I mean, why isn't every rocket sporting some sleek custom color scheme? Well, the answer actually starts deep inside the rocket with the super chilled cryogenic fuels. See, modern orbital launch vehicles rely on propellants like liquid oxygen, methane, and liquid hydrogen. To keep these gases in a liquid state so they can actually be pumped into an engine, they have to be chilled to extreme, sub-freezing temperatures. The catch? These cryogenics easily boil off into completely unusable gas if they absorb even incredibly small amounts of heat. To put those extremes into perspective, liquid hydrogen must be maintained at a staggering -252 degrees Celsius. That is substantially colder than even liquid oxygen or methane. Because it's so close to absolute zero, white paint is utilized as the default thermal shield. It basically acts as a giant mirror, reflecting the sun's harsh radiant heat away from those incredibly sensitive fuel tanks while the rocket waits on the pad. And this plays out in some pretty fascinating real-world scenarios across the globe. Take Europe's Ariane 5, for instance. Because it launches from French Guiana in South America, it absolutely has to be painted white to survive the intense tropical heat of that specific launch pad. And history has taught us some hard lessons here. When the early Soviet N-1 rocket prototype was rolled out in a dark gray color, it dangerously overheated the technicians who were literally working inside it. Similarly, NASA's Saturn V test article initially featured a black interstage that got way too hot sitting in the Florida sun. Both of these programs were forced to quickly swap out their dark panels for white ones.
Part 1. The Orange Secret. Stripping the Shuttle.
Okay, so let's look at the ultimate trade-off in aerospace engineering, balancing thermal protection against the absolute necessity of saving weight. For the first two space shuttle flights, STS-1 and STS-2, the massive external fuel tanks were painted a gleaming bright white. At the time, engineers totally believed the paint was necessary to protect the tank and its insulation from damaging ultraviolet rays during those long extended periods out on the launch pad. But as data came back from those initial flights, the engineers realized something major. The paint wasn't actually vital. They could fly safely without it. By ditching the paint starting on mission STS-3, NASA exposed the natural rust orange-colored spray-on foam insulation underneath. And amazingly, that decision shed roughly 600 pounds of dead weight from the launch vehicle. Now that foam is incredibly important, by the way. It shields the supercooled liquid hydrogen and oxygen from liftoff heat and stops dangerous ice from forming. This brilliantly illustrates a core law of spaceflight. Every single ounce matters. By stripping away that white paint, engineers were able to trade 600 pounds of heavy aesthetic coating for 600 pounds of incredibly valuable scientific equipment, experiments, and crucial payload enhancements. That raw orange foam quickly became an enduring emblem of the space shuttle, proving for sure that functionality and performance will always be valued above looks.
Part 2. Flying in carbon black when white isn't right.
Because white paint adds weight, some modern rockets decide to buck the trend entirely. Take a look at Rocket Lab's Electron vehicle. As European Space Agency rocket scientist Kate Underhill points out, the Electron is completely black because, well, that is the natural color of its carbon composite fiber body. If you want to paint porous carbon fiber, you need a tremendous amount of heavy primer just to fill in the surface before you can even apply the paint. For a microlauncher like Electron, that weight penalty is an absolute mission killer, so they leave it naked. And you know, this wonderfully explains the completely fascinating, shape-shifting color phenomena of SpaceX's Falcon 9. You've probably seen it. The rocket takes off a frosty white, but when the booster lands, it's covered in this distinct, patchy black and white pattern. Why is that? Well, the super-chilled liquid oxygen tank builds up condensation on the pad, acting exactly like a cold glass of beer on a hot summer day. This forms a layer of frost and ice that acts as a temporary white paint. When the rocket launches and lands, engine soot bakes onto the metal, but that soot completely fails to stick to the frozen sections. So, when the ice melts away, boom, You're left with that iconic black and white soot pattern.
Part 3. Extreme deep space coatings, the micropalette.
Okay, we've talked about massive rockets. But what about the micro level? Once a spacecraft is actually up there in orbit, it's exposed to brutal extremes, blistering solar radiation on one side and the freezing void of space on the other. This is where thermal control coatings, or TCCs, come into play. These are specially formulated materials engineered with highly specific radiative properties. They're designed to either absorb or emit heat perfectly, which equalizes the internal temperatures so that delicate onboard equipment doesn't freeze solid or fry to a crisp. For high-temperature applications inside the spacecraft, you really need something that absorbs and emits heat efficiently. Companies like Akhtar in Israel manufacture highly advanced inorganic black coatings with awesome names like vacuum black and fractal black. Notice the numbers on these. These incredibly thin coatings achieve near-ideal infrared emissivity, reaching values over 98%. This allows engineers to expertly manage extreme heat exchange deep within the guts of a satellite. But honestly, it's not just about heat. It is strictly about survival. In low Earth orbit, spacecraft are relentlessly bombarded by highly reactive atomic oxygen. Testing shows that traditional organic paints, like your standard polyurethanes or acrylics, suffer massive erosion and mass loss when exposed to this environment. However, advanced inorganic black coatings and specific silicone-based white coatings actually stabilize. When bombarded, they react by forming a tough, protective, silica-like shield that stops further erosion right in its tracks. These high-tech coatings are put through absolute torture before they ever fly. I'm talking surviving brutal thermal vacuum cycling from -120 all the way up to a scorching +380 degrees Celsius without flaking or peeling. They are essential for suppressing stray light inside sensitive optical instruments and telescopes. And incredibly, as we look toward future missions to the Moon and Mars, specialized coatings are being tested that demonstrate a high resistance to highly abrasive, static-charged lunar dust sticking to them. That is a total game changer. Ultimately, what you should take away from this explainer is that the aesthetic look of space hardware is entirely dictated by physics. The transition from white paint to the raw orange foam of the space shuttle, the stark black carbon of the Electron, the frosty white condensation on a Falcon 9, and those pitch black microscopic layers inside a deep space satellite, they all tell a broader tale. It's a tale where functionality, safety, and performance are valued absolutely 100% above visual appeal. So the next time you're watching a live stream of a launch and you see a rocket gleaming on the pad, ask yourself, what is the color of this rocket really hiding? Is it fighting off tropical heat, shedding pounds for science, or covered in a temporary shield of frost? Because out there, the paint job is truly just the tip of the engineering iceberg.